Hello, everyone. Welcome to this IISc seminar talk. Today, we have with us Karthik, Abinav, Shankar Raman. So, Karthik obtained his BTech degree from CS at IIT Madras before moving on to University of Maryland College Park. He completed both his master's and PhD there. And during this time, he was quite prolific, working both with IBM and MSR. So presently, he's a research scientist working with Facebook, as you can see in the slide before you. His main focus areas at Facebook, or Meta as it's now called, are in algorithms, ML with safety and integrity, online advertising, and recommender systems. He has published at various venues like UAI, NeurIPS, ICML, AI Stats, and EC. His primary research interest revolves around bandits, causal inference, and online matching, with a broader span of research along algorithms, ML, data mining, and market design. Today, he speaks about one of his works that mixes three of his research interests, matching bandits and markets, with a talk titled "Decentralized Bandits in Matching Markets." So, without further ado, let me hand it to Karthik for his talk. All yours, Karthik.
Yeah, thanks for the introduction. Yeah, and so today I'm going to be talking about decentralized bandits in matching market. So this is joint work with Abhishek and Soumya. So let me motivate this problem by considering a classical example of recommender systems, right? So when we think of recommender systems, we think of the following. So we have a user who comes into the system. You have like, let's say, five, six items that you want to recommend to them. And then you have a large pool of corpus. And from that large pool of corpus, you show them the best five or best six items, right? But reality is a bit more different than that. So the reality looks something like this. So you have many users in the system, and you have many different items that you want to recommend. And typically, items in like the modern day recommender system are also like other people on the system, right? And then these users have some kind of preference over different content. Likewise, the content also has different preference over which type of users they want to show to. Right, and then your goal of a recommender system is like to deal with this huge corpus of various entities with like various preferences, and like you have bunch of objectives that you have as this platform that you want to kind of use to like kind of do the recommendation. So for like when we think of recommender systems in like say 2022, like the picture looks much more like the platforms don't make one recommendation to one user, right? Like it's like you're making like maybe trillions of recommendations to like billions of users in most big reasonable systems. So it's essentially like a marketplace of recommendations. So which means that like if you view it like a marketplace, then like you need to have like some supply, you have some demand. So typically your supply will call it as like all the content that you have that you want to recommend. And here you can think of content to be things that are being actively produced, right? So you can think of YouTube influencers who are actually producing their content, like putting in work and figuring out like whom to show, or like TikTok videos or whatever. And likewise, like users who are consuming, that's like they are like the demand side of the market. So like the reasons content producers are producing content is because like users are interacting with it, consuming it, and so on. And there's a preference on each side, which makes it, which induces competition, right? Like so, the influencers want to reach certain kind of people. Users have interest that they want to consume certain type of content. And as a platform, your goal is to match these content to users. Uh, Except that, like a lot of times, you don't even know the preference of each side, right? So you don't know what is happening. Like you don't know why certain users like prefer certain content, and likewise, you don't even know which when an influencer or when a content producer creates some content, like you have no clue like which kind of users will like it and so on. So you may have some hints, but you don't really know the full preference. And then like the goal of the platform is also not to maximize like immediate reward, right? Like you don't want to just care about one recommendation where like for this particular instance and this particular recommendation, you get long-term value after like many repeated interactions. So broadly, like this is how recommender systems like look like in the modern day. And kind of like the bunch of this talk will start from this kind of a motivation, but I will just abstract out all details and let's just kind of talk as a mathematical model. Um, right. So in this mathematical model, this is how the system looks like. So we have n agents. So you can think of each content or each procedure to be one of the agents. And then you have M arms. So your arms are like users here, right? And then you have some T steps of interaction. So you kind of repeatedly have an interactive game. At each step, each of the agent submits a request to the platform saying that an agent NI would like to pull arm MTI at time step T, right? And then after all the requests are obtained by the platform gives these requests to the arms. And then now the arms come back picking one of the agents, right? So for each, so look at each arm. So each arm will get maybe like 3 or 4 proposals and it'll just pick one of the agent among all of them. And typically it's the one that it has some internal preference and it picks the one with the highest internal preference and then sends the reward for that particular agent back to the platform. And then each of the accepted agents, they see some reward RRT. Basically, like it depends on the chosen arm that agent had, and all the other agents who proposed an arm but didn't get picked, they'll get reward 0, right? So this is the way the system is going to work. So like so the platform's job is just to coordinate these requests from both the agent side and like from the and coordinate the feedback from the arm side. Uh,
Karthik, quick question. Do we assume like the number of arms is much more than the number of agents, or vice versa? Like what's the
So
agent?
like you can think of them to be roughly similar. Like I think for a mental model you can assume like you can so you can assume that either n is like smaller than m or like roughly similar. So I think uh, that's the mental model to have.
Thank you.
Yeah. So yeah, I think, and then the goal of this the full system is to actually maximize or minimize the total regret. Sorry, that should be minimized. So yeah, you minimize the total regret of the system. So what does like regret of the system mean here, right? So after T steps, each of the agents would have received some certain set of rewards, and then you sum it up over all agents, their total reward that they got. And then similarly, you sum up the expected reward that all agents will get in like a stable matching. So because you have preference, so agents have preferences over the arms and arms have preferences over the agent. You can kind of you can construct a stable matching, which is kind of like an equilibrium for this system, right? So you look at each agent in that stable matching, and then see what is the expected reward they would get across t steps, right? Or like I mean, you can compute it for one step and multiply it by t, and then the difference between this optimal value and the total reward of the algorithm, which is like essentially sum of all agents at the reward of all agents at all time steps, right? So the difference between this is what you want to minimize as a platform. And then like the goal of designing schemes is going to be trying to minimize this regret. And then we'll kind of make some assumptions on like what class of algorithms we will work with, right? So uh, when we work with when we work with like some form of centralized algorithms, we I mean platform can do whatever it wants. But when we work with like some decentralized algorithms, what we'll assume is that each agent will play the same algorithm. So essentially, like it's you just have the exact same algorithm, and each agent is playing the same algorithm, right? Uh, yeah, so I think this is the setup, and maybe like I'll stop here and ask like if there are questions that you would want to ask. Is the model setup clear?
So, quick question, Karthik. So the rewards are like both arm and agent dependent. As in, when it's different when agent I pulls the, like, let's say arm A versus when some other agent J pulls the same arm. Or
Yeah, that's right. So the reward depends on the actual edge, so the arm and the agent.
okay, and so like just to get like a feel of the model, uh, even if it's a single arm, like the problem is different from the standard multi-arm bandit set because you have it's like a
That's
multi-agent version of
yeah,
or
that's right. So even a single arm would be different from a multi-arm bandit.
and the other extreme where you only have one agent and M arms, and that's the standard multi-arm bandit.
Yeah, that's right.
Okay. And the regret definition would again like boil back to the standard regret definition if you have a single agent.
Yeah, that's right.
But like I guess the only difference is that okay, well if there's only one arm, then if there's only one agent, then every arm would be happy to sort of yeah
Yeah, take it
take
if it's chosen, right?
okay. So it's like the best way to see it is like a bipartite graph, n cross n bipartite graph. Every round a matching is selected, rewards are drawn, and the optimal is the state the like you're considering the optimal as the best stable matching and not the
Yeah,
like the utilitarian optimal or like the welfare maximizing.
right. Exactly. Based on the chosen actions, like chosen arms, select the matching, and where the
Right.
matching is selected using the preference, and then rewards for those edges are shown.
Got it. And like again, the optimal is like sort of hindsight, so I don't really need to know the preferences upfront for any of like in the algorithm or like
Yeah.
maybe the
So right,
algorithm.
right. Yeah. Right. So you don't need to explicitly know it, but like kind of you will learn the preference along the way because you're trying to learn the reward, right? So I think so. The preferences are just kind of driven by the expected reward. So if you learn the preference, then you can kind of
Oh, okay. For both the arm and the um,
yeah,
agent.
right. So yeah, that's right. And yeah, so one detail here is that the preference for each agent over the arms and the preference for each arm over the agents, they could all be different. We'll come to a bit on like what kind of assumptions we'll need to actually prove some theorems, but like in the model, you can each of them can have different preferences,
Okay. And
and all of those preferences are driven by reward.
and sort of one final question. The definition of stability is the standard microeconomic, the Gill-Shapley definition of stability.
Yeah, exactly.
Okay.
That's the standard definition, right?
Okay. Got it. Thanks.
Hi, Karthik. One other question. So the ARM picks one agent amongst all the submitted ones based on maximum reward?
So based on its preference over the agents. So and
That's
that preference is governed by the expected reward of those edges.
So it is a reward maximizing. Okay. Is there any assurance that like there would be a certain optimum that is found? So I was thinking, like, for example, if all the agents want to, for some reason, want to pull arm one at time one or arm two
Right.
at time two. So, and this keeps happening that they keep selecting the same person because they don't know, they're not speaking to each other, or there's
Right.
no. Is that something that's possible at all, or somehow this system
Yeah.
goes into sleep?
Right. So you're right. So like you're kind of getting into the details of like exactly how this system would work. So if in a decentralized setting, like what you're saying can happen, like literally all agents can keep pulling the same arm and only one of them is seeing something. So we do allow like some amount of communication, and then you also want to kind of minimize the communication cost. So either you want to minimize the communication cost, or like a priori before the start, all agents can kind of assume like a fixed protocol that they're doing. And which is why I mentioned that in the decentralized setting, like the class of algorithms we allow is every agent plays the same protocol. So, and then as part of that protocol, you can bake in all these kind of contention resolution type of things.
I see. I see. Okay. Okay. Thank you.
Karthik, just to confirm, there are total n cross, like n times m distributions, right?
Right.
And so the preference for each arm is that dependent on the means of those distributions, or is it separate?
Yeah. Right. So it is consistent with the means of the distribution of the rewards. So on all the edges, if you knew the mean rewards, then those already govern the preference, basically.
Okay. Okay. Thank you.
Okay, so now, so let's kind of go into the detail like that we were touching upon, right? So in a multi-agent setting, you can kind of have two ways of looking at it, right? So one is the centralized version. So here in the centralized version, what typically one assumes is that like the ARM preference over all the agents is known to everyone. So so one set preference is known. So ARM1, what is their preference over agent? ARM2, what is their preference over agents, and so on. And then at each step, not only does an agent select an ARM tuple, but it gives to the platform a full ordering over the arms. So it essentially says like agent 3 prefers ARM2 first, then ARM3 next, and ARM4 next, and so on. And then like once you give this full preference to the platform's job is to compute a stable matching based on these preferences and pulls the arm based on these stable matching and then sends the reward back to the agent. Right. So this is a centralized setting where it's kind of like pretty kind of makes a lot of assumptions. So, but I think it's still an interesting like a first point to study, because it's like you want to kind of understand like what is possible with this problem, right? And then I think the decentralized is probably the more practical version of this in like, let's say a recommender system or something like that, where like the user preference over, or like the ARM preference over the agent is all private. So, I mean, you can learn it along the way, but before the start, it's all private. And then each agent only submits one ARM tuple, right? So they don't give any ordering over the arms and so on. And then platform job is just take all these agents pull the arm and just relay the reward back. So decentralized is like kind of what we have been discussing in the last slide, but I just want to mention the centralized setting, because like we'll kind of start with the centralized setting and then look at how to do decentralized version of it. And then, yeah, the important thing in decentralized version is that like we fix a scheme and all agents play that scheme, right? Yeah. So let's see like a bunch of like known results, like both centralized, decentralized, and then I just want to make sure like that like only 2 and 3 are what like I'm a co-author on. One is something that was done by other group of folks. So like what is possible here, right? So if the ARM preferences are general, so when I mean general, I mean that each ARM can have arbitrary preference over agents, and they can be different across different ARMs. So in the centralized setting, we can kind of get log T regret. And since it's all centralized, there is no agency not communicate among each other, right? And then like if you kind of want to get the most general ARM preference, which is every ARM has its own preference over the agents. In the decentralized version, we can only get something like log 1 plus epsilon T regret, where like for some epsilon greater than 0. So this is not optimal. So essentially, like you'll see in open questions that like making something like this optimal is still like unknown. And then here, the agent communication cost is like very little. So it's like O of 1 or something. And basically, like the only kind of communication you need to do is something around like synchronization and things like that, which typically a platform can do it for you. And then the two interesting parts are like essentially when we assume uniform ARM preference. So if you assume that each ARM has the same preference over agents, so that is all ARMs have the same preference, and then in the decentralized setting, then we can get O of log T regret. with like O of log T communication again. And then the kind of more general version of this is if we assume that the system has a unique stable matching, right? So in hindsight, if the stable matching is unique, then again we can get O of log T regret, and then again the communication cost is O of log T. And then like in the next parts of these talks, I'll give like a high level overview of each of these four results. Yeah, so let's kind of get started. So let's start with like the centralized setting, right? So recall that in the centralized setting, the way, yeah, sorry.
Sorry for interrupting, but the agent communication cost being O1 means that what does it exactly mean?
So it means that like agents don't have to like explicitly communicate things apart from like some synchronization in the beginning. So you will see like when you see the algorithm, you will realize like why certain things need communication, certain other things don't need communication, basically.
Okay.
Yeah, so I think like for so yeah, we'll maybe once the algorithm is kind of set up for each of these, then what is considered communication cost, I guess, would become clear, I guess. Uh, yeah, so let's start with the simplest setting. So in the simplest setting, the agents all provide a full ordering over the arms, and then like the platform computes the stable matching and brings it back, right? So the algorithm is like kind of almost natural as what you would try to do. So since kind of like I guess Siddharth already mentioned, this is like a generalization of multi-arm bandit. You just pick up the UCB algorithm of multi-arm bandits, and then you try to essentially see how it will work in a matching setting, right? So what you do is at each time step t, each agent just ranks it by the UCB function. So I just wrote down like what UCB function looks like in case like people haven't seen it before. But if you have seen it before, this is like technically just the UCB function. So this is the mean reward, and this is like the deviation term based on number of samples you've used to get the reward. Right, so each agent essentially ranks its arms based on the UCB score of the reward it's seen on each of those edges so far, and that's the ordering it gives it to the platform. And then like the platform just computes the stable matching and then returns the reward back on just the stable matching edges. And then the algorithm updates its UCB function for that edge. And then kind of this is how the algorithm proceeds. So the centralized version is like kind of just a pure generalization of how it would work if it was like one agent, except that each agent is doing this independently. Right, so that's how the algorithm works. And then to compute the regret bound, like you kind of have to see like how many times you're actually playing an edge that is not the actual edge in your hindsight stable matching. Right, you keep count of those things, and to kind of do that analysis of the count, you have to see like when is the UCB score of that particular edge higher than the other edge and got played. Right, so I think the in the standard bandit algorithm, you kind of only do the analysis of how like how many times you play an arm that is not your optimal arm. But here, like you also have to make sure of the fact that it actually got played, even though the score is higher, right? So you can do some like counting argument using like Hovding inequality or whatever, and then kind of get the log T regret bound. So one kind of point I want to mention here is that even though I keep mentioning O of log T in the previous slide and here, I'm actually deliberately hiding the constant. So the constant is kind of important for this problem. Right, so the constant actually here is like 1 over gap square. So where gap is the difference between any two, the minimum difference between any two mean rewards. So you have like, let's say n times m edges, and each edge has a mean reward. So the minimum difference between any of those, any pair of edges mean reward is the gap. And then the regret bound here depends as 1 over gap square compared to typical bandit algorithm where like the dependence is 1 over gap. And then I'll kind of show that that's also the best possible bound you can get because the lower bound is also 1 over gap square. Which is why I think I've hidden all of this out to keep it clean, right? Yeah, I think I'll just again stop here and kind of see if there are questions or like discussion that we want to have here on this slide.
And so you're calling it centralized because you're computing a stable matching in this context. Like,
Yeah. Two things. Yeah, computing a stable matching, and like you're also like each agent is actually giving an entire kind of like preference over all the arms.
okay.
But yeah, I think so.
And the arms
Sorry,
actually don't have a say here in the sense that they only get one agent to sort of courtesy the stable matching. They don't get to reject or like.
So they do, right. So basically, like before before the arms are even pulled, the platform does the pulling. So each arm only gets one agent. You're right. Like I guess that's what I mean.
So I guess like the question I'm trying to get to is that like so these scores tell me the preferences of the agents over the arms. What tells me the preferences of the arms over the agent? It's the same scores.
Yeah, so that is right. So no, it's not the same score. So that preference is is assumed to be known to the platform. So in the centralized setting, that is also known. So now you have both the preferences.
Okay, and like one final digression, and I'll like shut myself out. So so it's quite like those deferred acceptance, like those Gale-Shapley algorithms are like known to run like have a like quadratic runtime. Is it interesting to think about like nearly like much faster algorithms given these numeric scores? Like I'm wondering if that has been like finding stable matchings under like such scenario.
I
like
see.
maybe
So
sub-quadratic or like sorting time algorithms.
So are these like exact algorithms, or are these like approximate?
No, I'm wondering if there are such algorithms. Like, so okay, the question is that I mean, here do you just run Gale-Shapley, or is there a like a in terms of runtime? Is there a better algorithm for these contexts?
I see. Good question. So here we just assume there's some black box algorithm that can run the stable matching. So essentially, like let's say Gale-Shapley or something, we run it and we get it back. Okay. So the runtime itself is definitely, I think, an interesting aspect to study, like especially in a centralized setting. Uh, I think that's like if there are better algorithms for these kind of like approximate scores, right? Like and approximate preferences. Yeah, I think that would be definitely useful. So here it's like we don't even bother about runtime, etc.
Okay. No, I mean there are works that look at stable matching with numeric scores rather than just ordinal rankings. So that's why I asked. But I'm not like very familiar with the state of the art. But yeah, like, okay, thanks.
Got it. Right. So now let's kind of go into the decentralized setting, which like kind of is the more I would say practical version of things, because it's it's implementable and so on, right? So like the key challenges here are essentially a couple of things, right? So like unlike a bandit algorithm, like sometimes an agent can pull an arm and you don't get any feedback, right? So essentially there'll be collisions, and then like higher ranked agents will only get the reward, whereas the lower ranked agents get nothing. And then like I think the other thing is also that like just because you like a single agent by itself managed to find the best arm among its edges, that doesn't mean that like it has figured out the best action, because like the best action for it is actually its neighbor in the stable matching in hindsight. So that its goal is to kind of figure that out, and it cannot figure that out like without kind of knowing like preferences of other agents, and like it has to be aware that there are other agents in the system, right? So I think so all algorithmic design will kind of like adhere to make sure that these two challenges are somehow handled. uh, so let's start with like the most natural attempt, right? So like similar to centralized algorithm, you will probably just try and make sure each agent somehow independently keeps like a you just treat it as a zero reward realization. Let's assume that like also that we are the mental model we are thinking of is like all the arms have the same preference over the agents, right? So if you have that preference structure, then actually like for the highest ranked agent, it's the optimal algorithm because it's never going to get blocked, and then playing UCB is what it needs to do. But the issue is that like the other agents are actually going to be going to suffer due to many things. Like so, when the higher ranked agents are actually doing exploration, like the lower ranked agents in this algorithm are going to get different statistics. So even though like let's look at like maybe the neighbor in the stable matching of agent 2, right? So agent 2, if it played so the UCB score on that particular edge, its statistics is going to keep changing because like top agent is playing some exploration and this agent is getting blocked, and kind of like there are steps that you're actually skipping compared to like a bandit algorithm. So essentially like this kind of an just purely applying UCB is probably not going to work. But most of our algorithms are going to be still like play UCB and then kind of handle these kind of collisions, and essentially it's going to be like how do you do this contention resolution in a way that is both amenable to analysis as well as like you get optimal regret. So that's like how our class of algorithms is going to look like.
Uh,
So let's
quick question.
yeah.
For the for the agents who do not get selected, so do they know who's selected?
In the decentralized setting, you don't. So like if you were selected, you would know. Otherwise, you will just know that you got a collision or something. That's it.
Right, zero word, like, and you don't know more.
Yeah. So right. So let's first start with like the first result that I mentioned, which is that you have no structure on preference. So each arm can have arbitrary preference over the agent. So this is like a pretty suboptimal algorithm, but the point of like providing this algorithm is to actually show that like something like if you don't care about the exact polynomial on log, like log of 1 plus epsilon t, uh, I mean, it's fairly straightforward to get it, right? So that's really the point of showing this algorithm. So it's suboptimal in multiple ways. So firstly, like on the dependence on t itself, it's log of 1 plus epsilon t over log t, which I will show in the next few slides, and also like the dependence on gap term, which I meant, right? So in all the algorithms, and the lower bound is gap square, like 1 over gap square is the constant in the O. Whereas like in this algorithm it's something like 1 by 2 to the gap, right? So even it has an exponential dependence on gap, which is again like super suboptimal. So, but the point is that like this kind of algorithm will kind of at least set the base on like what kind of regret bonds you're kind of hoping to get. And then this algorithm is actually fairly simple. So right, so what it does is like you just divide your time steps by number of phases, and kind of you can coordinate what a new phase would look like, right? So in this case here, we've chosen an epsilon, and you have two steps. So you have some amount of pure exploration you're doing. So each agent is purely exploring different arms in some round robin fashion. So that way you can kind of make sure that there are no collisions during these kind of round robin phase. And then after that in that particular phase, that sub phase of exploration is done. Now with whatever statistics for that phase you got, use the empirical mean and just play Gale-Shapley algorithm. So like essentially each agent will just propose the one that is like that is its neighbor in the Gale-Shapley based on the ordered empirical means, right? So this is what I'm now going back to the communication cost. So the communication cost here essentially is like after this kind of exploration phase is done, like the platform needs to collect everybody's, I guess, arm preference and send it back to the players, right? So once that is done, you just play like now all agents know their arm preference, and then they play the Gale-Shapley matching. So this is like a very naive algorithm, but kind of you can already get like log of 1 plus epsilon t type of regret. So which means that like all kind of regret bonds that we'll be aiming for is log t actually, because like something slightly larger than log t is fairly trivial to get. Yeah, so then let's just kind of look at like how this kind of an analysis will look like, right? So it's basically like a combination of essentially like doing some counting with like standard tools in Bandit, right? Like hub density inequality and so on. So essentially, what we need to show is that like the regret is bounded by. First step is like how many times you make an error. Condition on the fact that like you're not colliding. So that you would get from like just keeping track of these empirical means and see deviations of those empirical means. And then like every time there's a collision, you assume that there is you don't get any reward. So like that's like the worst case regret bounding. And then like you also assume that your regret is one at each time step in all those exploration pools. And then kind of like the first term comes directly from Hefling's inequality. Number of collisions and number of exploration pools you can pretty much simply count based on epsilon and the definition of phase and so on. So at a high level, yeah, this is literally how the proof proceeds, which is again like as you would see, a lot of these proofs are fairly straightforward once you know like basic things like basic tools in Bandit, right? So the interesting parts here are actually the model and the algorithms. So which is I've kept the proof at a very high level. Yeah, so I think this is like the kind of motivating the decentralized setting, right? So you can kind of get log of 1 plus epsilon t regret bound with maybe linear exponential dependence on gap in a fairly straightforward manner. So now let me go into the more interesting aspects, right? So how to get log t regret without like with like the optimal dependence on gap. So to do this, we won't be able to do it in a very general setting. So we'll have to start making assumptions on preferences now, right? So let's look at the first kind of assumption that we have where we can prove something non-trivial. So the first assumption is essentially this kind of uniform valuation. So essentially, there's a global preference over the agent for all arms, meaning that like each arm's preference over the agent is the same. So from an agent's point of view, this makes the problem easy because it's like all it has to like each agent can coordinate among themselves and over sometimes just figure out what that preference is. And then once you figure that preference out, like at least one side of the graph's preference is all known. So now like kind of agents can focus on just their end of the or like the agent's side of the market to like figure out their preference. And then I think the second thing this kind of preference leads to is like the fact that there's going to be a unique stable matching under this preference. So if there's a unique stable matching, like the advantage is that like now you're truly kind of just changing the definition of best arm, right? So that's all you're doing. So it's not even like there are multiple best arms, and you may have to see based on how other agents are moving, which of these would end up being the best arm in hindsight, right? So in a unique stable matching setting, all those kind of issues are also resolved. So which is why like that's really the motivation for like kind of getting the kind of assumptions we are starting to place. Okay, so in this scenario, like what we're going to do is like again we are going to be playing UCD, but we are going to be playing it in phases, and we are also going to have a subset of arms. So each agent, so there'll be like some exponentially increasing phases. At the beginning of each phase, each agent is going to keep a set of active arms, and it will only play from those active arms for this phase, right? And then the way it will play is it will use UCD on all the rewards it's seen for those arms. And then at the end of the phase, we assume that there's a communication setup. So the communication can either like you could kind of like either be in a truly decentralized setting where like there's no explicit communication allowed. Then you can kind of have a protocol that will essentially communicate certain information that you want. Or you can, of course, assume that like you can let the platform broadcast things and communication happens via the platform. I will go over like what kind of skills you will need and what you need to communicate in just a bit. But just to kind of put it out there, like the communication itself is not the most interesting part. I mean, like of course you need to communicate something. How you communicate it is not really the interesting part. So and in most practical scenarios, you can just let the platform broadcast things. Like it's not the interesting part at all here. Yeah, and then what happens is after the end of the phase, an agent removes the best arm of the higher preferred agent. So that is what is communicated in the communication phase. So each agent just communicates one arm to all its other agents. So let me go a bit more deep into like how exactly things look, right? So they're basically like some m rounds of sorry, this needs to be capital N. So there are n rounds of round robin phase. So since there's just a global ordering of arms over the agents, like within like the first n rounds, like you can easily get what that ordering is. So you can imagine basically like uh, so you, all agents play the first arm for n steps. Or rather, like in the out of the n rounds, in the first round, all agents play arm one, right? So now the best agent knows its preference in the arm's preference. Then in the next step, that agent can just essentially not play an arm or like play a dummy arm, and then the rest all play arm two. And then now the agent two will know its ranking and so on. So within n steps, you can pretty much figure out what the arms global preferences over the agents. So you can kind of like assume that that is known, even though we say it's private. Like I mean, within n rounds you can get it. So then the next part is where like this exponentially increasing phase kind of algorithm is happening. So like basically like as I said, within each phase you have a notion of active arms, and that notion of active arms is essentially in the previous phase, for agent I, all agents ranked above it, like 1 to I minus 1, they all communicated each of their best arms in that phase. So in the next phase, this agent just removes those arms, right? And then it plays UCB with its remaining active set of arms. So it's a fairly local of its active arm can essentially come back again in a phase later, because like in the previous phase now it was part of probably exploration, which is why best arm was something else, and then now that agent removed it and so on. Right. So I will maybe stop here and like kind of see like if the algorithm makes sense, and then kind of take any questions that you have on the algorithm itself.
I have a question here. Maybe you can clarify it, or maybe the question doesn't make sense. You can clarify it. So you said like in this first n rounds, what happens is like let's say all agents decided to play arm one, and then
Right.
let's say one chooses agent one, let's say for this
Right.
one, and then agent one goes out of the picture. But it could so happen that this agent one is getting more reward from some other arm. So let's say arm K or arm 4, something like that. And then we'll never realize that we'll never get to know that arm 4 has a very high reward for agent 1. Is that something that's possible?
Right. So the goal of this first step is just to understand this arms preference over agents. So like these are all like the scenario that you are mentioning, that it will eventually figure out in the rest of the steps. So the first M step is so if you go back here, like the primary assumption we are making is that all arms have the same preference over the agents, right? The goal of that first M step is to just get this preference feed.
That assumption takes care of my question. Yeah. Okay.
Right. Yeah. So yeah, I think and then the algorithm is kind of fairly natural for these kind of settings actually. Like so, these kind of phased based algorithms with like uh, exponentially increasing phase length is again not something that is kind of very new to bandits, right? Like I think a lot of bandit algorithms do proceed in such phases. So for instance, like one kind of obvious things that maybe you have heard of is like if you did not know the total time step and you want to get any time regret, like algorithms are of the same nature. So essentially, like anytime you have some quantity that you think you don't know, and that quantity is critical to compute your hindsight reward, right? And that quantity is not just a mean reward. Like the first kind of step to try is doing some kind of phase-based approach. Like that's essentially what we try here, and kind of show that the regret bounds are optimal here. Yeah, so let me quickly mention something about this, the non-interesting part, which is, or actually let me just skip it and I'll probably give the slides, you can just read it. Right? So I think if the platform is not allowed to do explicit communication, then there's a way to coordinate among all the agents. And similar to how we did this coordination of n rounds to figure out the rank, each agent can also communicate its best arm in the previous phase to all other agents during the communication phase just by playing arms and kind of exploiting collisions in a positive sense. But this is like kind of not that interesting because you can assume communication is a black box and platform can do it, for instance. So in interest of time, I'll just skip this. And then I'll just kind of like tell like the actual dependence on all quantities, right? So far I've been kind of hiding everything. So this is where we see all the quantities. So it's of course like all dependence on n and k is like quadratic. So meaning that it's n times k, where n is agent, k is number of arms, or like it's n square or k square, whichever is maximum. It depends on all these three things. And this kind of dependence is again natural. You would think, right? So like because if n equal to 1, which is the bandit setting, k log t is the best dependence. And then so like you would hope to get that even dependence on number of agents should be n. And then the important part here is that this dependence here, which is gap, right, which is different as the minimum between any two mean rewards. That dependence is log the gap square instead of gap, and this is the best possible. So you can kind of set up simple like two agent two arm examples, and you can't do better than gap square information theoretically. So in some sense, this is optimal in all parameters. Of course, like to get this, we have to place a strong assumption on preference, but up to that. And then like one kind of interesting thing here is that so again like in the previous setup, you kind of that is coming due to deviations from mean of while computing UCB and so on. And this thing is primarily dominated by the number of collisions. So somehow like that is the hardest part of the problem. That's when two agents are picking the same arm and you are missing out on things. So and kind of the algorithm reflects that fact while analyzing a regret as well. But yeah, I think that's the story here. And then like kind of it also has another neat property that I want to mention, and I'll kind of motivate why this property is important. So as I said, so the regulator is like essentially decomposed into two parts. Like anytime there's a collision, we assume that that regulator is one for that answer for that agent, and the suboptimal pulls, which is coming from Karthik inequality, like standard bandit analysis, right? The way we analyze the number of collisions is actually the fact that like so let's assume when I mean agent I, it's also its rank for the corresponding arm. The way the entire algorithm dynamics works out is that agent one is the one that first figures out its best edge in the stable matching, and then it's agent two, and then it's agent three, and so on. Right? So like so here's like a pictorial view of what I mean. So agent. So here the y-axis is the arm index, and each of these is picture for each of the agent. And then in the stable matching, agent one maps to arm one, agent two maps to arm two, and so on. So you can see that like agent one is the one that first quickly figures out like its best arm. Then it's agent two, then it's agent three, then it's agent four, and then finally it's agent five, right? So this kind of property is actually pretty useful in like a lot of recommender systems where it's like you want your best content to actually be surfaced out very quickly, and kind of it's making the optimal distribution in the system before like the other contents. So this is kind of like this kind of an algorithm is actually like very amenable to like those kind of other properties that you desire, even though like we don't explicitly place any of these things as a constraint on the algorithm. The way the algorithm naturally lands to its dynamics looks very favorable. Uh, yeah, I think I will kind of pause here and again like see if there are any questions.
Hi. So I had another question. So in this phase one of the algorithm where you're just trying to get preference over arms, Does that lead
Right.
to some constant regret terms?
Yeah, so that's a term independent of t, right? So it's like some constant which doesn't depend on t. Yeah,
Which is
it's an
not
additive term.
okay.
Yeah, yeah. So yeah, I think so. When I mean, I guess the like upper bounded by this plus this, I mean all terms that depend on t. So
Right. Yeah, yeah,
yeah.
understood.
Uh, Yeah, I think maybe we have like maybe about 6 or so minutes. So I will briefly mention.
Karthik, maybe one like quick question. So,
Yeah.
so like there is no sort of underlying assumption that even in this case that the arms have a like a uniform ranking over the agents, or like the
Sorry,
arms
so
can have.
that you mean agents over the arms? No.
So the uniform is only from the agents towards the arms, not the other way.
Oh no, the uniform is only arms towards the agent and not the other way.
And so and it's in fact not even a numeric, it's just that the preference ordering is the same. It's not like the means could be different, it's just that they're ordered in the same.
Yeah, exactly, right.
And so I guess like if I even simplify it further, like I assume there's some unknown but singular ranking of the agents for the arms, and also from the arms to the agents there's a single ranking. Then are there like so even the like stable matching question is quite interesting, right? Like I mean, forget regret. I just have these rankings, and I have like the preferences are stochastic, so noisy, if you will, and like figuring out, understanding if I can identify a stable matching or a near stable matching in like subquadratic sample complexity. That would be a like,
Yeah, right. Yeah, I think like it's interesting even in that sense of like the way you mentioned it, that like it's not trivial even if the both sides preference are the same and you want like super fast algorithms that will converge. So I think I guess what you're kind of getting at is at the fact that like you're saying somehow this kind of an algorithm is actually approximately computing a stable matching, or like the other way of saying it, with low sample complexity, it's getting like some like close to epsilon errors, actually stable matching, and kind of what right I say yeah, and you're saying that like even if both sides preference are the same, like fast stable matching algorithms are probably not known, and somehow this can get there. Is that your point?
yes, exactly. Yeah, like
I see.
yeah. In fact,
Right.
you are
Interesting.
like doing it right. Like you are getting a
Yeah.
near stable matching in a sample efficient manner without the, but yeah, like for general stable matchings, I think there are like query bounds no, like so it's not in the stochastic setting, but the in query models where you query like an edge and understand the ranking.
Right.
So there, like it's known that you essentially have to like there are almost like quadratic like NK lower, like essentially NK lower bounds, but
Right.
with this ordering, like a uniform ordering assumption and with some sort of error allowed, I think it's a,
Right.
to my mind, it's a nice question.
I see. Interesting. I didn't really think, like, we never thought of it in that, like, in an algorithmic sense of computing the stable matching itself. You may be right, though, that, like, this could, like, there may be, like, ways to analyze that. So, though this is not lesser than quadratic, right? Because I think it's still quadratic, but I guess your point is, can we make it lesser than quadratic by putting that assumption as well in?
Exactly. Yeah. Yeah. Almost. Yeah.
Right. Got it. Yeah, I think yeah, that's actually a very good perspective. We have never really even thought of those kind of perspectives.
Okay. But yeah, great. Yeah. Thanks.
Yeah. Yeah, I think in kind of interest of time, I'll just skip the next part. So it's essentially like we kind of are able to extend it to the most strongest sufficient condition for unique stable matching, which is called uniqueness consistency. So this, like at a high level, what it means is that if you have a stable matching, and if you arbitrarily remove a subset of agents and remove their stable match pair from the system, the rest of the stable matching doesn't change. So this is like somehow like the most strongest known sufficient condition for like when does a unique stable matching exist. And under this kind of a preference profile, again, like we kind of design some algorithm. So it's almost similar to what we had before, but we also need some form of like local deletion as well to like do some contention resolution and so on. Yeah, in the interest of time, I'm going to skip all of these things and kind of just stop at like some open questions. So again, some of these things are very like bandit specific open questions, but I think like Siddharth already had like other perspectives, which are also like in my mind very interesting and like probably open, right? So here, like essentially, like can we get anything in a decentralized setting with no assumptions on the preferences, right? Or like much more looser assumptions on the preferences. And then I think the next or the more important question from a more practical sense that in my mind is actually the contextual version, right? So right now there's agents, there's arms, and there's reward and so on. So like, but typically like each of these edges are associated with some large context, which is dependent on both the agent and the arm. And kind of like the reward is a function of this context. So you can think of, I don't know, like large models that are doing some form of content understanding, some form of user understanding, and then kind of their embeddings are shown to you before you actually make the matching. And kind of like, how do you optimize in that setup? Like, how do you even define stable matching and so on? So essentially the contextual version of this problem is like pretty open and interesting. And then I think kind of like another flip side to all of these is like something like called as fairness of exposure, right? So we are viewing all of this from a platform side, and in particular, platform is like content side, right? So on the user side, like can we make sure that like a lot of, so when you implement some of these things, each pull of an arm is equivalent to like showing users some content and then getting feedback from them. So can you somehow also deal with constraint like a particular user shouldn't be seeing too many agent requests that are suboptimal and so on. Again, like kind of actually concretely defining what this is and like solving it is like fairly open and I would say very interesting from at least like a very practical sense. So yeah, I'll stop here and kind of like we're over time. So yeah.
Thanks, Karthik, for the wonderful talk. I think all of us got some very interesting ideas from this because it mixes online learning, matching, as well as bandits. So congratulations for the talk. Now we are open to questions.
I have one question. Hi, Karthik. So, one thing I wanted to ask is, are there other notions of regret also that are common in this, like the multi-agent setting? Besides, here it's defined with respect to with respect to an optimal, which is the stable reward of the stable matching. But are there other regret notions too?
Yeah, so like some typical like other things in like purely decentralized settings without like such matching structure is like a max min or min max type of things, right? Like essentially each agent has its own agent specific regret, and then like you take the maximum regret as the total regret or something like that, right? Or like average of those agent regrets and so on. So that's another notion that like people use in like purely decentralized multi-agent settings. But
Okay.
again, there's no this matching structure and so on. So here, like the regret really depends on that equilibrium.
Okay. Okay. Thank you.
Karthik, I had a couple of questions. If you can go to the previous slide on, I think the open question slide, it's related to that. Two things. One is on a slight extension of the model itself. So maybe you can tell me whether it's worthwhile looking at this or not. As of now, a video can choose only one, or a content can choose only one agent to be shown to. But in the real world, I think it's a many to one setting where like content can be shown to multiple users at once, and then like the perspective goes away. And related to this, the fairness of exposure also, the question on fairness of exposure is slightly changed from what's written here, that each user should get at least one agent requesting for it. each as in every user to see at least one video or one thing. Yeah. So are these interesting questions? Are they tractable?
Yeah, I think that's definitely very interesting. Like, I think in the sense the combinatorial part of things that you mentioned, right? Like, yeah, I think they are like super practical as well. So, and I would assume they should be tractable, like in the sense in some sense of the tractability, they should definitely be solvable and definitely interesting as well. So, yeah, I think that's another open question. I would say if you're interested, you should try it out.
Yeah, stability would be an issue. Like when you have this, it's called the hospital resident problem. Like when you have like many to one matching, like Gale shap, like the universal existence of stable matchings, B matchings or many to one sort of go out. But yeah, maybe for these numeric settings, something can be defined.
Right. So you can still compare it against the like many to one, like one to one stable matching somehow, right? Like
Yeah, so this is yeah, like yeah, yeah, I'm not saying it's like a nail in the coffin, but like the a very like rigid extension of this like many to one matching is this hospitals to residents matching, which is like a single hospital can have many residents. So which is like a single user can be sort of shown many ads. In that like many to one settings, like stability is not guaranteed. Like
I see.
the Gale Shapley utopia is lost.
Got it. So the notion of system equilibrium should probably be something else in some sense.
Yeah, I mean, there are like, I mean, there are relaxations, but yeah, like not like so one has to be a bit like, yeah, forgiving it and defining the optimum.
Right. Makes sense.
Can you speak like just a couple of like how do you measure fairness in this context, like the third bullet point?
Yeah. So okay. So this is not like well formed from a mathematical point of view, but I can kind of give like what I mean by this, right? So this is essentially like another constraint that you're adding, right? So you're kind of adding a constraint that uh, when like let's say so, okay, so let's talk it. Let's kind of from a more practical point of view, like the way you would implement these things is like whenever the agents are giving request to a platform, the platform will show everything that the agent has to the arms. Whereas like now you can imagine another operation before that, where like let's say there are 5 agents who want to put one arm. The only feedback the agent gets is not collision, but it also gets another feedback which is saying that it didn't even go till the arms because like it was not even in the top 5 or top k or something like that, right? So you have this extra information. Like how do you use this kind of extra information in like in a setting that actually like kind of improves things? So that's really like the motivation of that last bullet point. Basically, it's like you're not just getting collision information; you're also getting whether you're in the top k or not for this user.
Okay.
Oh, okay, I'll stop recording now. Maybe we can continue the discussion after I stop the recording. Is that fine?
Yeah, sure.